Okay, this is a video that's going to show us how to calculate an equilibrium constant if we are given an equilibrium value for an equation. And so let's take a look at what we have here. We have a reaction where we have 2 moles of SO3 are reacting with 2 moles of SO2, or decomposing into 2 moles of SO2, sulfur dioxide, and 1 mole of O2. We say we initially charge a vessel with 500 or 0.5 atmosphere of SO3. There's our initial concentration of SO3, and it's allowed to decompose. So just to make sure we know what's going on here, so we're starting off with 0.5 here, and we're letting this reaction go to the right. And so that means the concentration of SO2 is going to be increasing, and the concentration of O2 will also be increasing, and then the concentration of SO3 will be decreasing. Okay, let's see what else we have here. So we know that we're starting off with 0.500 atm of SO3, and we don't have any of this at time 0. That's our initial. Then it tells us at equilibrium, SO3 is measured as 0.2 atm, so it's going to be 0.200 atm. Okay, so we now know one of our equilibrium values, which is a good thing, so we can easily calculate all the other stuff. So what we want to do is, first off, we're going to find our change. Remember, C stands for change, because the change line is where we can use the stoichiometry to calculate all the other changes, which then we can use to calculate the equilibrium values. So obviously, when you start off with 0.5 and you decrease to 0.2, the amount of decrease we have is going to be 0.300 atm. I just subtracted 0.5 and 0.2 from 0.5 to get 0.3. So from our change line now, we know that that we decreased 0.3 atmospheres in the SO3 gas, and we're going to use that for some stoichiometry. So let's go 0.300 atm, and that is for our SO3, and we're going to calculate what this value is here. And so we're going to use the coefficients of the balance equation. We have 2SO2 and we have 2SO3, and obviously with a 2-to-2 ratio, this value is going to be the same, 0.300. And so we have that value now. Now, an important thing to note is because, as we said before, this reaction is traveling to the right, this value is being subtracted here, but this value is going to be added here. We're increasing by 0.3. Okay. Now what we're going to do is take that same starting value, 0.300 atm of SO3, and we're going to calculate the amount of oxygen made. So we have 1 mole of O2 from the balanced equation, and we have 2 moles of SO3, and you can see that that's basically half the value. So we're going to have 0.150 atm there. Again, this is also going to be gained because the reaction is shifting to the right. And now what we need to do is we just need to add up our values here. And so we're going to have 0.300 atm as one of our products and 0.150 atm as the other product. Okay, now those are important values, those three values. This is the E line, right? And from our E line, our equilibrium line, we can take these 3 values and we can use them to calculate our Kp value. Now I'm going to write my Kp expression. Kp is going to be equal to, we remember that our products, so I can use brackets here because we're talking about pressure, of our sulfur dioxide gas. We're going to raise that to second power because we have an exponent of 2 multiplied by O2 to the first power, all divided by SO3 raised to the second power. So now what we're going to do is we're going to plug in our equilibrium line so we can calculate our Kp. So for SO2, it's going to be 0.3. We have to remember to square it because that's what was given in our Kp expression. We have 0.15, and we're going to divide it by 0.2, and that value is going to be squared as well. And so let's go ahead and scroll this down a little bit and run this through our calculator here and see what we come up with. Okay, so I'm going to go ahead and you can do all this math in your calculator at once. I'm just going to go ahead and square my 0.3, so that's going to give me 0.09 multiplied by 0.150. I just squared my 0.3 from right here and right here. And then I'm going to divide that by 0.2, which is going to be squared, and it's going to be 0.04. And then I'm going to go ahead and multiply through here, and I'm going to get a value of 0.338. No units on that, and that is my Kp value. Now, because that value is less than 1, that's going to tell me that my reactants concentration of my reactants are greater than my concentration of products. If the products were greater, then we'd be greater than 1, but not by a whole lot. And so that is one of the ways we can calculate Kp, and we could convert this to Kc if we wanted, because we do have the temperature, but we're not going to do that right now. That's how we're going to calculate if we're given an equilibrium value.